So this lecture is kind of going to be an introduction to the next couple lectures we have on earthquakes and volcanoes. So there's going to be a couple things in here that may be repeated, but in more detail later. Don't worry. So this is chapter 5, Tectonics, and it's about movement. So plate tectonics, by the way, play this, it's a GIF. Before 1960, the idea of plate tectonics was a very new concept, and it wasn't actually believed, meaning it was highly debated in scientific circles. So up until 1960, scientists saw oceans as being very large basins, and continents were just large land masses, and that was it. They were fixed, and there was no movement whatsoever, which we all know doesn't really make much sense. So the idea of tectonic movement and that it was plates was new and inventive, and initially came about in 1600, but wasn't until 1915 when Alfred Wegener wrote The Origin of Continents and Oceans. Here he outlined his hypothesis of what we know as continental drift. And he stated that Africa, South America, North America, Eurasia, and India, Australia, Antarctic all fit into one large landmass at one point, which is what this GIF represents, and he called it Pangea. He went on to say that during the Mesozoic era, like 200 million years ago, the supercontinent began to separate and eventually formed what we see today. Modern scientists have also surmised that this isn't the only massive landmass that have formed. The pushing together of continents and pulling away is a Wilson cycle, and they believe that this has happened multiple times before Pangea. So, how do we know Pangea was actually real? Well, we can physically match up continents to each other based primarily off of their continental shelves. So when you look at a globe, you're going to see, we're just going to draw a continent. It's going to be awful, but bear with me. So we're going to draw a continent. This is a continent, we're pretending. And so this is the landmass we see in the dark blue. Out in the water, we will see a lighter shade of blue forming around it. That is the edge of the continent itself. That is the continental shelf, which we will be learning about more in the oceanography section. So we can, based off of these shelves, fit continents together. And geologists studying, for example, the Blue Ridge Mountains or the Appalachians and other regions of the world have determined that there is ground mass that isn't the same as the rest of the mountain range. This indicates that when continents crash together, forming the supercontinent Pangea, in the case of Africa, we had pieces left off on the US. And we can see this in England, we can see this in Eurasia, that there are mountains or bits and pieces of other continents like clinging to each other, and it's super cool. So this occurred when this crashing together occurred, we have all this pushing, okay, and mountain building forms, and so this forms metamorphic activity because we have a lot of pressure going on in mountain building, and that leads to heat. Imagine this. The Blue Ridge Mountains were once the North American coastline. So let's pretend this is North America. I know it's not. It's a made-up continent. That isn't any continent. But we're going to pretend for now it's North America. We had Africa crash into North America, and all these mountains popped up because the coastline was pushed inwards. Here's our coastline. African continent, Kapoosh. And then it pulls away and leaves a little bit behind. Okay, so once the North American coastline, and the reason we know this is because we found limestone, we found shells, ancient critters that would have been in the ocean are there. We've also been able to discern that the same ancient creatures have lived all over Europe, Africa, Asia, Australia, Antarctica, South America, and North America, which would indicate that during dinosaur time, or a good chunk of it anyway, that the continents were connected, allowing them to run all over the place, essentially. later speciation that we see, certain species of birds that were not there, vice versa, happened after the continents split too far for travel to occur, which forced these species to adapt to their new surroundings and become different species altogether. So you're saying, oh, well, they're coastlines, they're underwater. So once upon a time, the sea level was actually lower, but also once upon a time, the sea level was higher. So we have a whole bunch of different things happening where we know in parts of North America there were shallow seas, and other parts of North America were desert, and today are not desert, they're actually forest, and etc. And so we know that where these continents may have connected, there may have been shallow oceans, but there may have been points where there was no ocean there and it allowed for things to cross back and forth. So yeah, it's not like dinosaurs had boats. And so we see that it did this. So we could see these are what I meant by little shallow oceans and lakes. They would have been either salt or freshwater, but they're pretty shallow and they're easy to get around. But we were able to see things like the Mesosaurus, the Lystrosaurus, Glossopteris, just all over, moving everywhere, and we're finding them on continents that are now too far away for this to be physically possible. So scientists try to explain fossils in different ways, including rafting, that they had clung to something and managed to raft across the ocean, Isthmian links, which we do know existed. We also know them as land bridges. And we know that there was an Isthmian link between Alaska and Russia at one point. So that's how we surmise that the early peoples of America, North America and South America, came to the US, came to the Americas in the first place. And it is definitely possible that mammoths could have traveled back and forth that way too before it disappeared, because they formed during ice ages because a lot of water has been trapped up in these glaciers, causing a drop in sea level. Another one is island stepping stones, and this one always gets me because they just show horses hopping back and forth, and I just imagine unicorns hopping around, going between, and goats, and that's how we got between everything. And then the last idea we have is continental drift, where, of course, these two were once in a relationship. They were mates of some sort, and now they're heartbroken because continental drift happened so fast. Which I believe they have an Ice Age movie about the continental drift. So since geologists have determined rocks being left behind, we're also able to look and see similar coastlines between continents like North America, Europe, Africa, and Greenland. So for example, the Appalachians and Africa, the British Isles and Caledonian Mountains and Greenland. And this is how we know that they were once together. And we're able to see that mountain building occurred on both sides as they came up. So how do plates move? When we think tides, we think oceans, right? So in the hypothesis was that there were tides of a sort, except it's deep down in the asthenosphere. So when the hypothesis of continental drift was met with a lot of debate, scientists were like, oh, well, how do they move? And Wegener was like, oh, tides. Continents break through the oceanic crust, and yeah, that's totally how it works. And he was a little bit right. So he was kind of right. We do have a current system, the asthenosphere. And this is the theory of plate tectonics. And so after World War II, oceanic explorers discovered an oceanic ridge system in the Pacific where we have the Ring of Fire, and in the Pacific is the Mid-Atlantic Ridge. Basically, there are volcanic systems forming at the edge of plate boundaries. Sorry, in the Atlantic, we have the Mid-Atlantic Ridge. But around the edge of the Pacific plate is all these plate boundaries, and we have a whole bunch of volcanoes around there. So contrary to popular belief, the Ring of Fire is not one connected volcanic system. Whoever has told you this is lying to you. if one volcano goes off, it does not mean another volcano is going to go off somewhere else. It just so happens that when you look at a picture of the layout of all these volcanoes, it makes a ring. So they call it the Ring of Fire. Okay, so the Ring of Fire, as we can see here, again, it kind of makes the outline of a ring. We're going to go into more detail when we get to volcanoes and in earthquakes a little bit. So the fire of the ring is active volcanoes along the edge of the Pacific Plate and other plates such as the Nazca Plate, the Cocos Plate, but generally we're looking at the Pacific Plate. So the ring is a product of plate subduction. So in the case of Pangea, we had two plates coming together forming mountains. But in the case of the Ring of Fire, we have two plates coming together. One goes underneath and it forms volcanoes. And this is called subduction. And so we call these zones subduction zones. So subduction zones will destroy material, and so they're known as convergent boundaries. And this is where oceanic and even continental, in some instances, continental crust goes underneath other crust, forming a subduction zone, leading to volcanic arcs, such as Japan. The New Zealand, Indonesia, the Philippines. This is also how we get the Aleutian Islands off the coast of Alaska. This is how we get the Cascade region. This is also how we get trenches like the Marianas Trench and the Aleutian Trench. Hotspots, though, like Hawaii. Hotspots are very different. Hotspots occur in the middle of a plate and have nothing to do with subduction. Okay, completely separate. Okay, so the lithosphere sits on top of the asthenosphere, right? So they're kind of like layers in a cake. And the lithosphere is the uppermost part of the Earth. It consists of the crust and the upper mantle. So if we were to look at a chart, that is the crust. Here is this in here will make up the upper mantle. And then down here, we'll have the lower mantle or the asthenosphere. And then we will have the outer core and the inner core. Okay, so our lithosphere is going to be made up a very thin piece on the top of the world, which is known as the crust. This is what we live on. Okay, very thin. Okay, and then underneath it we have the the upper mantle, and so combined they make the lithosphere. The asthenosphere is what's directly below that. So the asthenosphere is more or less molten. So it behaves like a liquid, but is essentially kind of solidish still. But it flows, it reacts to strain like liquid does. And so it's weaker, it has a more fluid flow, and the uppermost part of the crust, which is made up of oceanic and crustal lithosphere and crust, is about 100 kilometers thick in the ocean. It's very dense, and the continental can be 150 to 200 kilometers thick and is more felsic or light-colored minerals. And so that top part, that lithosphere, kind of floats on top of the asthenosphere. And the asthenosphere has these things called advection currents. And these advection currents, if I could find my mouse, that would be very helpful. There we go. These advection currents do this. And so they cause plate movement the same way waves in an ocean do. So blah, 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 blah. So the lithosphere responds to stress, same way a solid does. It will break and bend. Whereas the asthenosphere will respond kind of fluid-like under stress. Think of like think of slime. Not the sticky slime, but like the consistency. So it's independent from the lithosphere. It forms currents. So we have currents. And the plates sort of float and move along with these fluid motions that are made underneath it. And it kind of looks like this. So this is our crust, our continental crust, and our lithosphere. Okay, so when we have subduction occurring, and under here is the asthenosphere. So here's the difference: continental lithosphere, oceanic lithosphere. Okay, this one is much taller, but for the most part, what we can see here is that the asthenosphere, or a weaker level, isn't this dark color. It's kind of red, meaning that it's warm, whereas this looks pretty like dirt, what we expect the upper mantle to look like. It's pretty hard, it's brittle, it's rigid, it's going to bend and break more than just blub, 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 blub along. And this is what we essentially look at. So right now there are 7 major plates making up about 94% of the Earth. There are a total of about 16, but we're not really going to pay attention to all of them because some of them are very small, and they are currently shrinking even more because of subduction, like the Pacific, Caribbean, and Nazca plates. So there are 3 different types of major plate boundary. We have a spreading center, which is known as a divergent plate boundary. This one creates new seafloor. We have the subduction zone, which is the convergent plate boundary, which destroys. And then we have transform plate boundaries, which neither create or destroy. They kind of move side to side. And they're kind of neat. So because of these, you're going to have a variety of different types of volcanic systems going on. At the spreading center, you're going to end up with stuff moves this way, magma upwells and pours out, versus here in the subduction zone, where instead of that, it's going to be more along the lines of, hey, let's have a volcanic arc. So what we're going to do here is we're going to subduct, we're going to heat. That warm liquid rock will rise because now it's less dense than the surrounding rock, and it will form a volcano. So divergent boundaries are constructive margins. Okay, they create. We see seafloor spreading here, the creation of new seafloor. There we go. So creation of new seafloor with divergent and constructive. Plates move apart, like we can see here. Plates move apart, and magma comes up and moves out. Eruptions are non-explosive, and they push the seafloor apart because it's moving with those asthenospheric currents, as well as new magma coming up and being pulled out by gravity. Convergent boundaries are destructive. They destroy. Generally, we see them at subduction zones. One plate goes under the other, it forms volcanoes, and then you can also see one where it builds mountains because the 2 plates buckle instead of one subducting. So it leaves us with 3 types of convergent boundary. We have continental and continental, which gives us mountains. We have continental and oceanic, which gives us volcanic island arcs. So where you'll get an island with a volcano on it. And then we have oceanic versus oceanic. Oh, I'm sorry. I made a mistake there. Continental and oceanic do not make onto island arcs. Ugh, I'm so dumb. Continental and oceanic, what you'll do is you'll have a coastline, you'll have subduction underneath, and volcanoes pop up on the coastline, like what we see on the east coast, or the west coast of the United States. With oceanic versus oceanic, that's when you'll get a volcanic island arc, where you'll have a bunch of islands with volcanoes, like Japan. Transform boundaries are conservative. They neither create nor destroy. you have two plates moving past each other in an active system. So you don't have new lithosphere being made or destroyed in the process, but what we can see here is a change, right? We have maybe at one point this was a straight line, but due to this movement, that line has been interrupted and now continues over here. So divergent boundaries are also known as spreading centers. Okay, spreading centers. So they are essentially ridges. They form the largest mountain ranges in the entire world. Their eruptions non-explosive, push the seafloor apart. They form one of the longest topographic features on Earth. It actually covers 20% of the Earth's surface, and it's one gigantic mountain range. The crests of the volcanoes are about 2 to 3 kilometers higher than the basin adjacent to it, and they can be about 1,000 to 4,000 kilometers wide. They're huge. And they form a rift valley due to tension forces. And we can see this occurring on the surface in one major place, Iceland. The average rate of seafloor spreading is about 5 centimeters per year. Which is about 2 inches per year. That's pretty fast if you think about it. New lithosphere is pretty hot. It does move farther away from the spreading center due to asthenospheric currents, as well as additional upwelling pushing it out. The farther away it moves, the cooler it gets and the denser it becomes, partially because it will be affected by seawater, but also because it cools more and more and more. So thickness has to do with age. Even though it's spreading, it doesn't mean it's spreading evenly. When this occurs on land, So while they're spreading, it's not like, oh, we're moving all together very quickly. Great. No. The spreading center may move at 2 inches per year or 5 centimeters per year, but maybe farther out. So here we see that 5 centimeters of movement. Maybe over here we're only moving 2 centimeters of movement. Okay, what does that mean? It means you're going to have a traffic jam. So things are going to kind of like crumple and bunch up together as they're trying to move along. And so that will create thicker ocean floor and denser. Continental rifting. So continental rifting, like what's occurring at Iceland, is when you have a spreading center on land. This occurs when a divergent boundary forms on a continent. Another example is the East African Rift that is occurring. Here the boundary is isolated, and when this occurs, eventually a new ocean basin is formed. But in Iceland, it just so happens that it just happens to fall on the ridge and the spreading center itself as the Atlantic Ocean continues to open. But in the East African Rift Zone, what we're seeing is we're having a new spreading center, meaning a new ocean will open in there. The lithosphere will stretch and thin, and eventually it breaks into large blocks as it continues to spread, and eventually magma upwells, and we have more spreading, and eventually an ocean forms. And by soon, I mean thousands of years. Geologic time, millions of billions, so 1,000 is pretty quick relative to that. So here's the example of the Icelandic boundary, and we can see that it's literally the mid-ocean ridge just goes right through it. Super neat. And the other one is the East African Rift, but I don't think I have one for that. I'm sorry. But this is an example of how upwelling over time, when you have it working on a continent itself, going from you have upwarping where you have a bump forming, we have movement out, eventually it breaks as they're moving. Water will fall in as upwelling continues and pushing away, and eventually you kind of get what's called a linear sea, like the present day Red Sea, and then we'll have an actual deep ocean basin. Convergent plate boundaries happen when two plates move towards each other. One plate is denser than the other. Okay, one equals more dense, which leads it to subduct under the other. So once that happens, the subducting plate heats, and if we're looking at things like oceanic versus oceanic, or oceanic versus continental, that oceanic crust has been chemically changed by the fact that it is in contact with salt water. And so it becomes saturated with water, which decreases its temperature for melting and its pressure. So it is able to melt at a much higher place in the asthenosphere than most dry magmas, most dry rocks would melt. And so this leads to this melting, which again, hot and melted, makes it less dense than cold, rigid rock. It will rise using cracks and eventually form a continental volcanic arc. Okay. When you have oceanic versus oceanic, one will be more dense than the other. Maybe it's older, maybe it's absorbed more seawater. Either way, it's more dense. And in this case, you'll have the same exact thing happen, but instead of it being a continental island arc, you end up with a volcanic island arc. Which means you have all these little islands filled with volcanoes on them. In both cases, you're going to see a trench form. And these are very deep portions of the ocean. It's where subduction is actively occurring. It is pretty neat. When it comes to continental collisions, you're going to see that maybe at one point it was oceanic versus oceanic, or continental versus oceanic, where the continent was coming up to the continent, oceanic was subducting, and then eventually it gets to the other continent. And so this subduction kind of ends. And instead we have the continent pushing up against the other continent, and you get mountains forming. And that's what we see here. So our example for each of these, the Cascades, like Mount Hood in Oregon, Japan for our island arcs, and the Himalayas. So again, continental versus oceanic, oceanic versus oceanic, continental versus continental. All right, so continental plus ocean. Example, Aleutian Islands. Continental versus continental. Example, the Himalayas, okay, Himalaya Mountains, where we see that India and this whole plate is moving towards Eurasia. We have oceanic lithosphere subducting, and then the India plate collides with the Eurasian plate, and we just see this massive mountain range forming. And it is still forming today because India is still continuing to push into the Eurasian plate. And so there is a lot of earthquakes there because the Himalayas are still forming. So moving on to transform boundaries, there are known transform faults and like massive transform faults, and one of these is the San Andreas fault. San Andreas. The San Andreas is actually a plate boundary, and it is a transform fault. So the oceanic zone area, when you have transform boundaries, you end up with transportation of oceanic crust. So like a subduction zone. But it doesn't break the crust or create new lithosphere. Instead, you have all these linear breaks in the sea floor. And this is going to be a plate boundary. So they don't spread or form magma, but they're pretty inactive in that form. But they move things towards their doom, essentially. So like the Juan de Fuca plate of the Cascade subduction zone looking all funky, the reason for that is because of all of these. The Mid-Atlantic Ridge looks super weird. It's not a straight line, and it's because it has all these transform faults. So it helps move plates around. It helps move material to subduction zones. It helps move the Mid-Atlantic Ridge so that it's able to spread versus one straight line, which may not work so well. So it offsets ridges, and it is a fossilized trace, which is pretty cool. So here's the Juan de Fuca plate, which is currently being subducted underneath the west coast of the U.S., so California. And this is all transform boundaries, all of these, and they form little faults. And it's part of the reason why the Juan de Fuca plate isn't one nice square, and it's all kind of like chicka 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 chicka. And then we have the San Andreas fault right here. This is a fantastic example of a transform boundary against the Pacific plate and the North American plate. So this means the breakup of Pangea did what? It formed the Atlantic Ocean. It had a Wilson cycle. It formed the Red Sea. Evidence we have that this is really what is happening. We have multiple. Big ones are going to be deep sea drilling, mantle plumes and hotspots, and paleomagnetism. So when magma erupts, it does so at what is called the Curie temperature. This means it has nothing magnetic yet. So the grains will align to form a magnetic field when it's cooling, meaning it will show which direction is north when you look at it. So we can determine north and south at the time of its formation, which is paleomagnetism. And so we're able to see, one, that poles change over time. At some point, the North Pole is not going to be the North Pole anymore. It will have switched and it will be the South Pole. Not geographically, magnetically. And we can actually watch these shifts in the ocean floor. And how we know that there are these shifts is because if there was only one rock there that cooled once, we would only have one north and one south ever. We wouldn't ever know that we had switches, which means that the floor is moving, it's spreading. So we use these magnetic reversals to determine a magnetic time scale. Changes are divided into about 1 million years, known as crins, and have ever finer reversals within a cron, or 100 years, or 100,000 years, I think. So these end up forming magnetic stripes in the seafloor, which support seafloor spreading, according to Vine and Matthews. Deep sea drilling. Sediment in oceanic crust has fossils, so we dated them and eventually got the guts to ask how old they were. Yeah. So sediment age increases with distance from the mid-ocean ridge. Mantle plumes and hotspots. So remember, a hotspot is an area of volcanism that occurs within a plate, not on the edge, such as the island of Hawaii. And the Hawaiian Islands are all volcanic, meaning hotspots don't move. The only way for there to be multiple volcanoes is if the plate moved. So here is core samples to show the thickness of sediments increasing with distance from the ridge. Here we see hotspot volcanism, okay? So each of these has volcanism at some point, okay? Hawaii just recently had another eruption that ended sometime last year. I believe it was Mauna Loa that erupted again. We actually have an extension of the coastline in many areas. It's cool. But this mantle plume doesn't move. It's the plate that moves, so we can see which direction the plate movement is. And so this is another way that we can see polarity, and we know that it changed, and it's not our imaginations in the ocean floor. And that is because we can also see the magnetic time scale in volcanic eruptions. And so we're able to actually see it along these spreading centers, where we see here we'll have one, maybe north is this way, south is this way, in these pink zones. North is this way and south is this way, and then it goes back and forth and back and forth. So we're able to see how often the magnetic poles switch. And we call this normal and reverse polarity. And we can also see it in other plates, such as the Pacific plate, the Juan de Fuca plate, where we have the Juan de Fuca Ridge, which was a spreading center. So plate movement forces include convection, slab pull, and ridge push. So we know water boils, and we know how water boils. We know that warm water rises and cold water sinks, and this is known as convection. Okay. I hope at least we all learned what convection was in chemistry class. It is a type of heat transfer that involves the movement of less dense warm water up and more dense cold water down. Okay, and it forms a current. Okay, and in many ways, it means it is stirring itself in order to even out temperature. The same thing does happen in the asthenosphere, where we have a really warm, hot fluid rock, which will then heat parts of the lithosphere. You'll have melt forming, and that will rise up just as the same time as we have slabs being subducted down, and these are the cold, which we have here. So I'm going to draw this out really quick. We'll see convection. We know that we have this happening because we have our hot material moving up, and at the same time, we have our cold material moving down, hence convection. We also have ridge push and slab pull. Ridge push is a gravity-driven force that results from the elevated position of the ridge. So as magma comes up, it pushes itself down and out as more magma comes up. Okay, and it is a driving force of momentum. Because you're heavy, you sink like dropping a rock in water or water into a cup of oil. Ridge push, however, is all gravity related. So it's the weight of itself that causes the lithosphere to slide down a ridge, basically pushing the ocean floor apart as new magma comes up. But there is movement. There is also resistance, like friction. So all of these work together. There isn't just one. This means that subduction is the downward driving force of this convection. And so this is where we see slab pull. So slab pull results from the sinking of a cold, dense slab of oceanic lithosphere and is the major driving force of plate motion. So again, we have our hot moving up and our cold moving down. And we see the driving forces of convection. And so from this, we end up with two models for the Earth. The whole mantle model, which is the first one, you see cold subducted slabs can sink to the core mantle boundary, which is this. And that's pretty deep. And so this allows for mantle plumes to start close to the core and rise up like this. So just because we agree now that we have this movement doesn't mean everybody agrees on how. So this is just the first model. So the second of the two models is the layer cake model. And in this one, we see a thin layer for the upper mantle, which is this, an even thinner layer for the crust, and a very thick lower mantle or asthenosphere. Okay, slabs in this particular one. Whew, getting a thunderstorm. Slabs in this particular one do not sink past 1,000 kilometers, meaning they don't breach the asthenosphere-lithosphere boundary. They may be at the boundary, but they don't go really past that. And they're going to melt around there and come back up as a mantle plume. You're going to see that mantle plumes start at the boundary between the asthenosphere and the lithosphere and come up. We're also going to see melts just starting at the lower end of the lithosphere as they are heated from the asthenosphere and coming up. And we do even have some circumstances where we do see the asthenospheric melts coming up, but those are rare. So yeah, that is it. That is the end of the tectonics lecture. I hope you guys all stay safe. Please make sure to listen to this. It does go along with earthquakes. It does go along with volcanoes. You will need this. Make sure you fill out information in the study guide and post any questions you have from the study guide. I hope you guys have a safe week.